Okay, so our next speaker is Elli Pomoni, who's going to tell us about exploring thermal CFTs.
Thank you very much. And I want to thank the organizers for the fantastic organizations of Eurostrings this year. It's amazing to have so many people, and for having me here, of course. And this is a more formal talk than before. And I want to ask a very basic question. I want to start from first principles and ask if I can turn on the temperature and still be able to calculate. And we will be super in equilibrium. And I have to say that this is work with fantastic collaborators. Enrico Maceto is somewhere here in the audience. And Alessio is applying this year, so keep an eye for him. He's really fantastic. And let me, actually in this audience there is no need for motivation. We already had talks, many talks for black holes. And if we really want to use the ADS CFT, we should really learn how to turn on the temperature and really learn how to calculate. Also, quantum critical points, now they are seen in the lab, and we know that they are at finite temperature. So if we want to be able to calculate, we need to learn how to do it. And of course, there are more formal, more nerdy reasons. We want to be able to do quantum field theory in different manifolds, and I like that also. Okay, first of all, textbook material. You choose your favorite finite temperature quantum field theory book. The first thing they teach you is you put your quantum field theory not on flat space. You have one circle, which is the Matsubara circle, and the radius of this is the inverse temperature. And you put periodic boundary conditions for the bosons and anti-periodic for the fermions, and you go. You compute your Feynman diagrams with this prescription. Now we want to do more. We want to use what we have learned from the bootstrap. So in this talk, I am going to assume that our bootstrap friends did their work, and they have given us the CFT data. They have given us a set of conformal dimensions and 3-point functions. And now I am interested, given this data, can I now produce the finite temperature data, which are encoded in thermal 1-point functions. So this is a neutral scalar operator, but generically, any symmetric traceless operator can acquire a VEV. Yes? So I want to learn how to calculate these B's. Now, another thing that works for us is that we can still use the OP, like in normal bootstrap. And here I have the form of the OP. There is only one thing to keep in mind, and at the beginning when I started playing with this, I made so many mistakes, that now the radius of convergence is finite. So whatever calculation you do, you need to keep this in mind, otherwise it will be wrong. And an easy way to understand this, you can even imagine the two-dimensional cylinder. If you are surrounding your 2 points with a ball, the ball should never cross itself. This is an easy way to say why this is like that. Now, not only we have the OP, we can now insert it. We can insert it in a 2-point function. Let's take two identical scalars. I insert the OP, and I see that I have on the right-hand side these guys that now acquire VEVs. So what I can do, and these are symmetric traceless, so I can use the Gegenbauer polynomials and write 2-point functions in this form. And now these combinations, the particular combination of the 1-point function with the 3-point, these are the unknown things that we need to learn how to calculate. Yes? So the name of the problem is learn how to calculate these A's. We have one more thing going on for us. And this is this goes under the name of the KMS relation from Kubo, Martin, and Schwinger. And this is that the 2-point function, and of course higher point functions, they have this periodicity property. You can shift tau by beta. Now, doing that is a condition that is not captured by this very nice form of the 2-point function. It doesn't obey this in any obvious way. So actually this condition is an extra condition we can impose on our 2-point functions. And you should now really think of this as the thermal crossing equation, which we will try to solve. Yes? So this is the beginning of the game. And of course, this formula can also be written by playing a little bit further with symmetries in a few different variations that for me will be important. Now, let's say up to now everything was known before I started playing, and now I come in, and I had to make choices because by now we have many results. So first I will show you how to derive thermal sum rules and how to check them at the beginning. Just check with the computer if this is satisfied. Then I will turn to heavy operators, and I will show you how to obtain the asymptotic density of the OP, of these A's. Then, this is very new. This happened basically the last month. I will show you how to start setting up the numerical bootstrap program for this thing, at least in a way that I like. Again, this will be very preliminary, but it shows that we can do it. And then I will talk a little bit about defects when we have a finite temperature. So let's start with the sum rules. So first of all, we start with KMS, and in particular, we start with KMS as it appeared in this paper. And the reason why we start with this is that we want to be inside the OPE regime. So the thing that I said one needs to be careful about. And with a little bit of manipulation, you can bring this equation in this form. Let's look at this form. All the bootstrap people, they recognize this is what they have been doing the whole life with a slightly different F here, which is given here. This is an equation that holds for any integer n and any odd integer L. So we have an infinite set of linear equations for this V, which is the data we want to calculate. Yes? But again, I stress this is a linear set of equations. Again, if you are a little bit familiar with Bootstrap, maybe you have seen the Gliozzi method, and here I just say this to tell you what is this L and M. You can think of it as taking derivative with respect to tau and also the R of the 2-point functions, and asking that in the end to obey the KMS condition. This problem, so is very similar to the way Gliozzi was thinking, but it's much simpler because of the fact that we know the zero temperature data, and thus this part of the equation is completely known. Yes? So we have, again, I said it, a linear set of equations for these combinations. There is one difficulty as opposed to the normal zero temperature bootstrap, which is that the fact that the 1-point functions here, they don't have to be positive, so we cannot just happily use linear programming. And then another further simplification which gives this very nice form of our sum rules. You can simply set the spatial coordinates to go to 0, and this sort of hard-looking equation becomes quite beautiful, and you can even play, with your fingers with this equation. There is only one catch when you set the spatial coordinates to go to 0, that operators with the same conformal dimension but different spins, they will sum in this form. However, usually this does not happen, that operators with different spin have the same conformal dimension in generic theories. This happens in free type theories. So, but then we know how to solve and we can take care of it. Yeah? Okay, so we have the sum rules, and first we test, and we also try to learn. So here are plots for 4-dimensional free theories, for which we know the answers, and the ON model in the Largen limit, which also we know the answers. And let's try to understand the plots first. First of all, we have these dashed lines here. These correspond to the left-hand side of the sum rule, which has to do with the identity contribution. Yes? And then we have these other lines with the dots, that they are the right-hand side. And what we are doing is we cut this sum to some operator delta, and we compute only up to then, and we see how well we are doing. Are we reaching the dashed line, yes or no? Yes, so this is what is happening. And the main lesson from looking at these plots is that especially when you look at the ones that correspond to small l, only with a few light operators, you can, in a very good approximation, reach your left-hand side. Let's keep this lesson, yes? Of course, if you want to go to higher L, things become harder and you need to keep more operators. But let's keep this lesson. Now we go to heavy operators. What tricks can we play there? So first of all, okay, the bootstrap people here, they know the Tauberian things very well, but I will try to present it in a very intuitive way. So let's begin, and here is the paper that most inspired us in this work. Let's begin by the two-point function, again at 0 special coordinates. First of all, you can write it, the Gegenbauer go away, and we have this very simple formula. And then we can introduce a spectral density, plug it in, and this is our form for the two-point function. Very nice. What do we do now? We need only one thing, actually. We need to know the locations of the poles of the two-point function in the real axis, and this is very easy. Here they are. Having them, let's do the following. First, we will make an ansatz. Again, I am making this ansatz because I also know Tauberian theory. You know, otherwise I would be more uneasy to do this. So the ansatz I'm making makes sense. So I will make this ansatz, the conformal dimension to some power and some overall coefficient. I plug it in and I do the integral. And then I match with the poles. That's all. Very simple. And here it is. This is the asymptotic form as delta goes to infinity of the OPE density. I already said it many times, the interpretation of this gadget is the asymptotic form we are picking up the heavy operators. But there is one thing to keep in mind. The physical spectrum is, of course, discrete. We have these deltas. So more correctly, the way to think is that actually we have the average density of the OPE operators, and this is precisely the object that obeys the Tauberian theorems. So this box is mathematically correct. And not only that, Tauberian theorems also give you the error that you are doing. So this is like the perfect formula. I come from a very formal background, so for me this formula makes me feel very happy. Yes, I know what error I am doing. The derivation I gave you is very heuristic. If you are interested, you can look in the paper. We have a formal derivation. And the formal derivation only needs 3 things. It needs unitarity, which translates to the reality of this. It needs boundedness, which we proved formally in the paper. Here I am just going to say one thing, what boundedness means, because usually people think that they need that the coefficients are positive. It is enough that is, it can be negative, but it's a finite negative. And what happens in our cases is that, okay, most of the operators, especially the heavy, they go positive, but there can be a few light operators that they get a minus value. So this also fits into the mathematical framework. And the third thing that I think, which we also have because of unitarity, I need that the delta of the external operator is higher than 1/2. This is very good from 3 dimensions and up. 3 dimensions we know how to do, we don't need anything. And 2 dimensions we know how to do with the conformal map, so we know how to do everything, yes? Now let's again a little bit plot and learn and play. So this is the exact 2-point function. We are in the 4D free theory. By the way, all of these things that I'm doing, you can do them in any free theory, any dimension, any 2-dimensional theory, no problem. And then from 3 dimensions on, this is where the game starts, yes? So first we test with free theory. Here you can extract the A's and you can plot them, and you can plot the Tauberian approximation, and it looks amazing. You can also just plot the 2-point function itself, and you can compare it with the Tauberian approximation. The one side of the Tauberian approximation comes from the heavy operators, and for the other side, you do KMS, and this is basically the identity contribution. So heavy operators map to the identity contribution, and that's how I get this very nice plot. And I am not going to explain details. Either you know what is the ON model or not. All I wanted to say is that Chatsev and friends, they have calculated over the years the 2-point function. And here I write it in one form. And okay, one nice thing that we did is because we were working with the zero spatial coordinates. When we plug in r equal to 0, we can write it in a very beautiful closed form, which is always satisfying. But not only that, we can make this very beautiful plot for ON model in the planar limit. So the red is a Tauberian approximation. The blue is the exact data. And you see very quickly they start matching. Yes? And you can play the same game with a 2-point function. You can plot the exact. You can plot the Tauberian approximation. And you see, actually, it is even unreasonable how well they match. But that's very good for us, because now we want to start setting up our numerical problem. And we will use what we have learned, all of these lessons that I said. So let's do it. Okay, first of all, our current approach is based on these papers, and some of them are quite recent, and is working very well for whatever we have tested up to now. And I really hope, because it's phrased in a very general way, that it will be possible to work with more theories. And also, for me, what is also very important, it's very simple. It's shift-enter. Every point is made in a few seconds, and a plot is made in a few minutes. So you don't need to have any, your laptop and a few minutes and you are good. Nothing fancy. So the input of our method is the zero temperature spectrum. So we need our bootstrap friends to give us the zero temperature spectrum of a theory. And the output is the 1-point functions that I was saying. A, again, is a 1-point function times the 3-point function. And there will be some other coefficients which will appear here in a second, which we'll also get. And what we do, I said it many times, the light operators, we can truncate them actually very quickly. Usually, up to all the examples that we have tested, we never had to go more than delta, more than 10. So it's really low. So we truncate this guy up to some delta H. This is something you have to play with your code a little bit to get the right number. And here, for the rest of the sum rule, you put the approximation, the Tauberian. Yes? And actually, because we really wanted to do it nicely, and if you don't, you will discover very quickly that you should, we not only put the Tauberian, we also put the corrections the way the mathematicians tells us that they should be. And we have unknown coefficients, which we get by minimization process. Yes? So what we do is we have our sum rule, and this has to be 0, and we minimize it with random coefficients. That's the name of the game. Okay, so now I will show you. I'm very stressed about this because this is super preliminary, but anyway, it's interesting, so I will go for it. So this is free theory. In some sense, it's not interesting at all. But if you can make a code that can do this in 3 minutes or 2 minutes, I would say this is amazing. So the circles are the exact results that we know. The red line is the Tauberian, which is also, I said before, it's too good to be true. And what we were missing, if you wish, is the light operators. But now, by this minimization process I described, we get them perfect. Yes, again, in a few minutes. Ising model, again, we know everything, but we are testing. Is this really good what we are doing? Yes, the answer is yes. So here is it. Tauberian approximation, which of course fails for the light operators. Look here, one guy is up there. The exact results are the circles, and the numerical results go in perfect. Again, with a few clicks. Okay, we start getting a little bit more to interesting things. This is a less good plot already because we didn't have enough time to make it go perfect, but you can already see the analytics that we know from Satzer is a red line, and the numerical dots are almost on it. Everything comes with an error bar that we are calculating, but there is no way in a 25-minute talk to tell you about error bars. But also there are error bars. So this is a planar error model. And here there is this amazing paper where they calculated for the Ising model. And this is this orange dot. So there are two ways with our way of doing it, with our program to do this. One is to use what we learned here and extrapolate, so the opposite of the planar limit. And this is what is shown in this plot. So this is our dot. And by the way, the Monte Carlo is also here. By the way, I am not saying that most probably the Monte Carlo is better than the Caltech group. Most probably the error bar that we have right now is big enough to have everyone in. But this is something that can be resolved because this plot was made in 10 minutes. Yes? And there is a second way. The bootstrap people have actually calculated the spectrum of the Ising model to perfection. So another way is to, again, just plug in the 3D Ising model and calculate directly, and this is what is happening now. So this is where we are. A tiny little bit about line defects. We have only 5 minutes, but we can do it. I mean, the reason why I, and I guess everyone here is interested, we want to study Polyakov loops, which are a criterion for confinement. That's what we want, right? So let's try to do. Okay, I'm not going to do any gauge theory today, but this is where we are going. So what do? We need one thing from our bootstrap friends, which is zero temperature data. We need the OPE of bulk to defect. We have an operator in the bulk, and we see when we throw it on the defect. So these O hats are the defect operators, yes? And this is completely known. When you do this and you plug in a one-point function of an operator, bulk operator with a Polyakov, what you get is an expansion. This is a formal expansion, but everything here that is underlined by blue is zero temperature data. And the only new finite temperature data are these one-point functions on the 1D defect CFT. That's the only new thing. And now we know, we play the same game, KMS. KMS with the presence of a Polyakov loop. Great. We do it, and we derive this sum rule, which is super similar as an equation with the equations that we were playing before, and we started developing all of these numerical things. For now, this equation we can only test for, baby theories for which we know analytics. But now the next step will be to go and study this numerically. Yes, that's the name of the game. Okay, so with that, I will start concluding. So what is the status first? So first of all, we have nice thermal sum rules written in my opinion, very useful ways, simple and useful ways. For the heavy operators, we can, using Tauberian theory, write down the asymptotic behavior of the OPE density. We have started setting up the numerical bootstrap for the thermal problem, and it looks, in my opinion, it looks very good. And also I presented how to study. It was super short, I know it's a whole paper, but how to start looking at temporal line defects. And of course, what the future includes, okay, first of all, we want to do the 3D Ising model nicely because we can compare with the Caltech group. But then, we want to do, of course, n equal to 4, we want to do a BJM. So, the production of papers. And if the code is good, it will be clicky, clicky. Yeah? Then, this geometry is very important. Because at least in the large gen, this is what Witten told us, there is a phase transition and we want to be able to study it. And I think everything that I said, of course it will be harder in this geometry, but it will not be much harder. So do that. And I think this way, and actually we have already started a little bit working on this. Can we say nice things about black hole hydrodynamics? I want to calculate it over S, doing this. Can I do that with CFT data? Yeah. And again, the numerical approach is a very important thing in this game. Yes.
Hey. Questions for Elli?
One right up front. And David first. Can you give some details about how you get the error bar?
In the like, it's not something that I can just say things now. No, over coffee. Yeah, sorry. But in some sense, you know this when you did your labs. The same way you learn how to minimize the chi-square and you calculate your. It's basically the same.
Yeah, you mentioned you want to compute eta over S.
Yes. Because it's the famous.
That's okay.
Yes.
But my question is that I think the difficulty there is that even if you know the Euclidean correlator,
Yeah.
to get eta over S, you have to, or eta, the difficulty is in the analytic continuation to Lorentzian.
Yes, I know. So what we have been doing for some months now, and it's actually not even just that in my mind, I really need to go to Fourier space to do this. So, okay, I don't know how fast we will be able to finish this. It depends on how hard we work. But in order to start doing any of these things, what we are doing is we're trying to formulate this problem in the momentum space. And I think this, like, let's say thermal bootstrap on momentum space. I think the moment this formalism, and now we are testing it on ADS3, blah, blah, blah. If this formalism goes, I think I will calculate. I mean, I don't know. This is how I am thinking now.
We can talk about it later.
Yeah.
Just a follow-up to that question.
Yes.
Even if you manage to figure out how the bootstrap works in momentum space, it's a bit counterintuitive because you are very much working in the OPE regime, where you, as you said, you have a finite radius of convergence,
Yes.
and hydrodynamic correlators, I usually think of them in the long wavelength.
Yeah, I understand, and that's not something I can just do, but I think I can do it. Yeah. Okay, I don't know how to give a better answer now. Yeah.
Okay, other questions?
I mean, here you assume that the zero temperature data are given.
Yes.
If you relax that condition, is that strong enough to also determine those?
So good. So, okay. In my mind, for the problem to be solvable, is we are here. Yes. This part is given by this. I need at least a few first light operators. 3, 4, something, but I need maybe 3 is all, but I need at least a few. Otherwise, there is nothing. Yeah.
Okay, are there any further questions?
Yeah, over here.
One of the equations that you wrote are rho of delta. As delta goes to infinity, it goes like A
Yes.
delta to the minus alpha.
Yes.
Can you explain this, if this is an assumption and whether
So
there are examples?
first of all, this I make, this comes from mathematical theorems, yes? But at the beginning, you can think that this is an assumption. You can plug it in your integral, you do your integral. Actually, this is the way I present it. It is super simple. And you basically get this by matching at the poles. Of course, this can also be proven formally. But at this level that I explained it is a heuristic. I start with a smart ansatz.
But not every CFT has this property. That
Every CFT has this property. This is a famous, every CFT has this property. There is an equivalent, not for the 2-point function. Maybe you know for the 4-point function, right? No, you don't know this. Every CFT has this property. This is a universal behavior. I cannot explain more.
Okay, any final questions? Going once, going twice? Okay, let's thank Elli again.